A pocket lighter can make a spark strong enough to cross air, even though it has no battery and no visible wires to a power source. The tension is simple. Air resists electric current, but one small click briefly creates thousands of volts. The trick is not stored electricity. It is a fast mechanical impact aimed at a material whose internal charges shift under stress. Now let's slow the click down. Inside the lighter, the important action is not the flame yet. It is the chain from your finger to a spring, to a sharp strike, to a crystal-like material, and finally, to the air gap where the spark appears. Each step changes the form of energy, but only for an instant. A lighter produces a visible spark without a battery, and the click is the energy source that starts the chain. In a quit-away view, your finger pushes the button, and that motion compresses a small spring inside the lighter. When the mechanism releases, the spring drives a tiny hammer forward, more like a sharp tap than a slow push. The hammer strikes a piezoelectric crystal, and for one brief moment, mechanical impact is converted into electrical voltage. This is different from a battery, which stores chemical electrical energy and releases it through a circuit. Metal contacts carry the short voltage pulse toward the spark gap, where two conductors sit close together near the gas outlet. Under ordinary conditions, the air gap between a lighter's metal electrodes behaves like an insulator. Electrons can move easily inside the metal tips, but they do not freely cross the gas between them. A voltage across that gap creates an electric field, which is the invisible push that acts on electric charge. At low voltage, the field only tugs weakly, so the air molecules stay mostly neutral and the gap remains closed to current. As the voltage climbs, the field can pull electrons away from some air molecules. This is ionization. Neutral molecules become charged particles with free electrons and positive ions mixed together. Those charged particles briefly form a narrow conductive path between the electrodes, like a tiny wire made from air itself. Certain crystals and ceramics create surface charge when they are squeezed, struck, or bent. Before compression, their positive and negative charge centers sit in a repeating pattern that nearly balances at the outer faces. When a force distorts the structure, those charge centers shift slightly, relative to each other inside each tiny unit of the material. This is not whole atoms marching across the crystal. It is a small internal offset in charge position. During compression, the balance changes, so one face shows a slight positive surface charge, and the opposite face shows a slight negative surface charge. That microscopic separation is the piezoelectric effect, and it gives a lighter the first ingredient for a spark. The spring and hammer turn a slow finger press into a fast, concentrated strike. First, your thumb pushes the lighter button downward, but that motion is too gradual to make a strong pulse by itself. The mechanism uses that slow motion to compress a small spring, storing mechanical energy for a moment. When an internal catch releases, the spring drives a tiny hammer forward much faster than your thumb moved. The hammer hits the piezoelectric ceramic, giving it a sudden jump in stress instead of a gentle squeeze. On a simple force over time graph, the finger press is broad and low, while the impact appears as a narrow spike. High voltage does not mean a piezo lighter is acting like a tiny battery. When the spring hammer hits the piezoelectric crystal, stress changes the positions of charged atoms by a very small amount. That separation produces only a tiny packet of charge, but because it is forced across the lighter's terminals almost instantly, the voltage can become very high. For a moment, the electric field across the spark gap becomes strong enough to tear electrons from air molecules and let a spark jump. A simplified comparison would show the piezo pulse as a tall, thin spike, while a battery output sits lower but lasts steadily over time. The piezo gives a brief shove, not a sustained supply. The spark has to form beside the nozzle, where fresh fuel is meeting air, not buried inside the lighter body. When the valve opens, butane leaves as a narrow jet and pulls surrounding air into the edges of that flow. The piezo element then sends a brief high voltage across the spark gap, enough to tear electrons from nearby molecules, For a fraction of a second, that gap becomes a thin ionized channel that carries current and heats very quickly. It is less like a battery powering a heater and more like a tiny hot thread placed in the mixture. Ignition starts only if the local fuel and air fall within a flammable range, and if the hot channel overlaps that mixture. A piezo lighter is reliable because its igniter does not need a charged battery to make it spark. Each click stores a little mechanical energy in a spring-loaded hammer, then releases it into a ceramic crystal. That sudden squeeze separates charge inside the crystal and creates a brief high voltage, metal contacts, and a short wire guide that pulse to the spark gap, where it jumps through air near the fuel mixture. The module stays compact because it makes one sharp pulse at a time. Instead of storing electrical energy for months, it is more like a sealed mechanical striker than a miniature electronic circuit. Piezoelectric materials link mechanical stress and electrical voltage, so the same crystal behavior can run in either direction. On the stress creates voltage side, grill igniters and gas stove igniters work much like a lighter. A spring impact squeezes a ceramic, separated charge appears on its faces, and a short high voltage pulse can jump a gap. Some sensors use the same direction more gently. A knock sensor, for example, turns engine vibration into a small voltage pattern instead of a spark. On the reverse side, buzzers and ultrasound transducers apply changing voltage to make the ceramic flex. That motion pushes air as sound, or sends pressure waves through gel and tissue during imaging. A modern piezo lighter turns a quick mechanical click into a brief high-voltage pulse. The impact stresses a piezoelectric material, shifting charge centers and creating opposite charges on its faces.